Hello there. So a brief introduction of myself. This is gonna be the first video that I'm gonna make for this channel. And what I'm gonna do in this video is I'm gonna solve the AMC12 A from 2021. Um, I myself have participated in this examination, so I'm kind of doing this like these problems by memory, like how I solved them during exams. And so I wouldn't be able to like know exactly the wording of the problem and also what the answer choices are. So I'm just gonna like solve it as I go, I guess. So the first problem from 2021 AMC12A is this problem. Usually in AMC12, the first 1 to 10, like the first 10 problems are usually like the most accessible ones. And therefore it's like usually a lot of people get them. And I'm not gonna spend a lot of time on these like problems like explaining because they're not like very, very difficult. So yeah. The first problem is this problem. What is 2 to the power of 1 plus 2 plus 3 minus 2 to the power of 1 plus 2 to the power of 2 and 2 to the power of 3? There's really not much to say about this problem. You can just do it like this. We know that 2 to the power of 6 is like 64. So we can get these answers instantly, and this is basically 50. The question number 2 is about, it's like a condition problem. So basically, it's asking for the condition when square root of a squared plus b squared is equals to a plus b. And there are a number of answer choices. Some of them are like something like, for example, when ab is equals to 0, when ab is equal to 0, and when a plus b is bigger than 0, something like that. And sometimes like a bigger than 0, bigger than 0. These are some of the answer choices. I couldn't remember all of them, so excuse me for that. Basically, this question is just you square both sides, and then like what you get is this equation. So you do complete this. No, it's not complete the square. You just expand the expression, and you eliminate the a square and b square. So what you get is 2ab equals to 0. So ab is equal to 0. However, we have to note that this is a square root, meaning that both sides have to be positive. So the condition is ab equals to 0, and when a plus b is bigger than 0, bigger or equal to 0 actually. So that's the answer. So the third problem, I kind of forgot. Sorry, I think it was like two numbers. Their sum is 17402, and one of them is a multiple of 10. So we can write it as, let's say this number is k. So 10 can divide k. And it's when this last digit is removed, you get the other number. So this question, I think, is pretty obvious because if you remove the 0 from this number, then you get this number divided by 10, basically. So we can set this number as, let's say we set this number as a, and a plus k is equals to 17402. And k is basically 10a. And we get a equals to 17402 divided by 11. And then we do some calculations. and we get 1582. And we're asked for the difference between the numbers. So basically 15820 minus 1582. Or you can just do 1582 times 9. It doesn't really make a difference. But in the end, you should get something like 4238. And that should be the answer. And for number 4, I think it was a logic problem. It's something about the snakes, 13 snakes, and 4 purple, and 5 are happy. So there are 3 conditions. The happy snakes can add. The purple snakes cannot subtract. And the snakes cannot subtract also means cannot add. So the key thing is, this is basically a logic problem. We know that the purple snakes cannot subtract. And we know that the snakes which cannot subtract they can also add. So basically we know that purple snakes also can't add. So basically we know that purple snakes are not happy snakes. That's basically the solution for this problem. And if you see, like, maybe you're just confused by this condition. In fact, AMC 12 always kind of, make these problems where they give you unnecessary information. You never should assume that every single information will be used. So a very typical problem, but I guess not really complicated. Number 5. Number 5 is a problem, I think, about some random dude who mistakenly entered a wrong number. So basically, I think he entered in his calculator 66 times 1.AB. 1.AB instead of 66 times 1.AB recurring. And the answer he got was smaller than the actual answer by 0.5. So our task here is to find AB. So basically, in this problem, there are 2 ways to solve it. One's, a good way to kind of simplify the problem. The other way is to, just kind of like bash it algebraically. I'm going to show the kind of the bashing way to do it. We always know that when we have digit recurring, this is basically the equivalent to AB divided by 99. If it's like 0.00 AB recurring, that's AB divided by 99 divided by 100. So something like that. And if we have, for example, ABC recurring, then it's the same, except we add 1 more 9. So this is something you should remember if you're doing the AMC. And basically, we use the kind of the same logic here. So we have 66 times 1 plus AB divided by, sorry about that, divided by 10, 100, sorry. And this is equals to 66 times 1 plus AB 99 minus 0.5. So the 66 cancels out. So we have this form. We rearrange the subjects. we get something like this. And we know we can group AB out, and we'll get this equation. So in fact, AB is just equals to 0.5 times 9900. So 5 times 990. Wait, sorry, I think I did something wrong here. Yeah, sorry. This is basically a typical mistake I always make. There's also, we have 66 here. So we group the 66 out as well. So we have 66AB equals to 5 times 990. And we get this equation, and obviously divide by 33. So this will be 75, and A equals to 7, B equals to 5. Another way of doing this is if you observe this equation, when you have 66 times 1.AB minus 1.AB, it's kind of like the same logic, but I just feel like it would be faster because 1.AB, AB minus 1.AB, you immediately get this equation. So immediately you know that 66 times AB divided by 9,900 times 66 equals 0.5, and we should get the same answer. It's a much faster process, I feel like. Yeah, so that's number 5. Number 6 is sorry, I don't think I recall the question, so I'm just gonna skip it. Number 7 is, I think it was something like xy minus 1 squared plus x plus y squared. And what is the minimum of this? So basically what you have is x squared y squared minus 2xy plus 1 plus x squared plus 2xy plus y squared. Well, I mean, maybe you will ask, like, why would you think of expanding first? So basically, if you observe this expression, you know there's a minus 2xy here, and you definitely know there's a plus 2xy here. Maybe you can cancel out some terms and simplify the expression. So what you're left with is x squared plus y squared plus x squared y squared plus 1, I think. If you see this expression, there's a very famous trick called the Simon's factoring trick. So basically what you want to do is you have x squared. You want to make x squared and y squared. You want to make 1 x squared because x squared times 1 is equals to x squared. And you also want to make 1 y squared. And coincidentally, you also have 1 here. So 1 times 1 equals 1. So this expression basically can be refactorized into this expression. And this is a very interesting expression because we know that x squared and y squared are, since they're squared numbers, that means they have a minimum value of 0 because squared numbers cannot be they cannot be negative unless you're talking about like imaginary numbers. But in this case, this doesn't apply because it's a real number. So immediately we know that the minimum value of this is 0. The minimum value of this is 0. So it's basically 1 times 1 equals 1. That's the answer for this one. The next problem I I think I didn't really solve it in the best way, because I basically used pattern finding, which is like usually what you would do if you don't really see a clear pattern. But if someone else sees like a better solution than mine, please feel free to actually tell me. So we have d0 equals to 0, d1 equals to 0, and dn equals to dn minus 1 plus dn minus 3 for n is bigger or equal to 2. So what are the even, like, how do you identify if d2021, d2022, and d2023 are even or odd? So basically, what I did was I basically just list out all the numbers, and let's do d2. d2 is basically I think, yeah, sorry, d2 is 1, and d3 we can just d3 is just d2 plus d0, so it's 1. d4 is d3 plus d1, 1. d5 is d4 plus d2, which is 2. d6 is d5 plus d3, which is 3. d7 is d7 is 3 plus 1, which is 4. d8 is 4 plus 2, which is 6. d9 is d8 plus d6, which is 9. And at this point, you will be you'll be able to see a pattern here, because this is even, even, odd, 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 even, odd. Even, odd, even, even, odd. And if you continue in a similar fashion, you'll find that d10 will be 9 plus 4, which is 13, and 13 is an odd number again. And you would not need to continue anymore, because if you observe this, this is even, even, odd, 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 even, odd. And you're basically, this every term is dependent on the previous term and the previous third term. So this term and this term, so even plus odd. And it's like, it's same as d3, even plus odd. So it will continue in a similar periodic fashion. And at this point, I actually realized that during the test, I made a huge mistake, because if you observe here, it's 1, 2, 3, 4, 5, 6, 7 as a period. So 7 terms in one period. So if you look at D2021, 2022, and 2023, 2021 is number 5. So if you look at this period, number 5 is odd. So the sequence should be odd, even, odd. In the test, hilariously, I actually assumed the period was 6, because I just saw this D6 thing, so I thought it's 6, but in fact it's 7, because I ignored the D0 term. So that was really unfortunate, but that's fine. For number 9, there's this very interesting problem where there's a clear pattern of multiplication of numbers. And actually in this, during my exam, I actually didn't know how to do it, but luckily I actually guessed the right answer. I'm sorry, I'm just really bad because like I'm not a very experienced competitor in math, so that's fine. So basically, if you observe this expression, this is 2 power of 1, 2 power of 2, 2 power of 4, 2 power of 8. So all of these powers are 2 to the power of n. So what can we really do about this? Here comes the kind of the trick where you would expect. It's a very elegant little trick for this problem. So basically, I think you guys know this equation. It's like we kind of use this idea to continue with this problem. So we notice that if we keep doing this, we also get like the same kind of power we have here. And it's also kind of a recursive sequence because this is here and this is here. So what we have here is the idea is basically to times the whole thing by 3 minus 2. And if you look at this kind of sequence now, it seems much clearer because this has now become 3 squared minus 2 squared, the difference of squares. And this has become 3 to the power 4 minus 2 to the power 4, and so on. So at the end, we will get this expression. So the answer will be 3 to the power of 128 minus 2 to the power of 128. Yeah, so that's a very fun problem. I actually tried out a few terms at the start, but I was without success. So a very elegant solution, I would say.